Morning, morning. I mean, not morning, afternoon.
How are you?
Ah, good. Last period of the day, guys. How excited are you guys?
Not very excited.
Not very. What's the last period?
I
What?
know, but Friday, has a bigger advantage.
Uh-huh. We're almost there. We're almost there. Are you guys excited to be back in school next year or what? Or you guys just want to stay home all the time? It's gonna happen because you are gonna probably gonna be able to get vaccinated over the summer. This is probably going to be a really big push over the summer to get everyone vaccinated. I mean, they already reduced the restrictions. Home is better. Hell no. Why would I want to socialize with others? I want to stay home. That's like, I guess. I can definitely understand why some people would rather stay home. But for the sake of learning, I think it's better for in school. Just for like learning purposes. If we're just talking about learning purposes, it's just a bit better for a physics teacher to be at school. Staying home has a greater advantage to learn. For physics, I don't know. I don't know. I don't know. I kind of just like moving. I mean, it's not moving is also one of the reasons my leg hurts. So it's like I have like an ulterior over there. It's gonna be nice. It's better than being home alone most of the time. Okay. Well, I'm 100% sure you guys are still going back to school. Like going back to school September. You can opt to stay home. You'll get different teachers though. If you opt to stay home, you'll get different teachers that choose to teach remote. I'm definitely not teaching remote. It's not happening.
Uh, Mr. Chan.
Yeah.
Uh, so the Grammy remote learning, but can I sometimes visit school?
What?
I mean, am I allowed to visit school?
Can you visit school? I
Yeah, I
don't.
mean, to meet my teachers and my friends.
Sure. Pretty sure you can. There's nothing stopping seniors from people from coming back, right? There's
And
nothing really stopping.
is there going to be a convocation?
Convocation?
Yeah, I mean, I'm senior, so I'm gonna be graduated in June.
People, graduates, alumni do come back. I've seen it in other schools. I've seen it in my school. I've seen it. Alumni do come back. It's also why there's like when you graduate university, there's like an alumni association, and I'm pretty sure there's an alumni association for John Adams. Nothing's preventing you from coming back to visit, obviously. All right, let's get started though, right? We do want to get started with this learning. So yesterday we talked about Hooke's law. We talked about how it's like we're not actually learning Hooke's law though. We are learning a different type of thing that's on your regions. We're learning about force on a spring. Force on a spring is something completely different than what Fs on Hooke's law is. Force on a spring is the force acting on the spring. If you're pulling on the spring, if you're pushing the spring, you are that force on that spring. Today, we're going to talk about something called elastic, or rather spring potential energy. And the easiest way to demonstrate that is if imagine yourself pulling back a rubber band, right? Let's say you're pulling back a rubber band or a bowstring, right? You're pulling back the bowstring, you're doing work, and the bowstring is being stretched. Can you guys hear my chair squeaking?
No, it's good.
No, it's okay. Okay. So good. Good. I'm glad you guys can't hear it screeching. So you're pulling the bowstring back and you're giving that bowstring a lot of potential energy. Can someone remind me, what do I mean by potential energy?
The potential to do work.
The potential to do work, being still. Okay. Yeah, the potential to do work. You have the ability to do work, right? Stored energy. Good, right? Stored energy. You have the ability to do work, but you just haven't done it yet. Right? The last example was, right, when I taught you guys about gravitational potential energy. Right? If a ball can definitely fall down. Right? A ball can definitely, the force due to gravity can definitely pull the ball down. But if the ball hasn't fallen yet, nothing is being done yet. So the ball has potential energy. If the ball has not fallen a certain distance, it has not done anything yet. So the ball has the potential to do something, right? It has the potential for the force of gravity to fall, but it hasn't done it yet. Same thing with elastic potential energy. When I pull my bowstring back, I haven't done anything yet. The bow is, if I were to release the bow, if I were to release the bowstring, the arrow will definitely fly forward. But I haven't let go yet. I have not let go yet. After I release the bowstring, what does my potential energy turn into? Something definitely has to happen. Kinetic energy of what? Kinetic energy of what? What has the kinetic energy? What is kinetic energy? First off,
Power.
no, not power. Kinetic energy is not power. I thought, no, there's no way you don't know this, John. Okay, actually, that's bad of me to say. What is kinetic energy, guys? Let's be serious now. Let me be serious. What is kinetic energy? This is really worrisome.
1/2 mass velocity squared.
Okay, that's a mathematical formula. Okay, yeah, that's 1/2 mass v squared. So basically, what is it? When do I have kinetic energy? Energy and motion. Yeah, energy and motion. So if you're moving, you have kinetic energy. So what's moving here? What has the kinetic energy? The arrow. Yes. Finally. Yes, the arrow has it. No, not the bow doesn't have the kinetic energy. I guess you can think of it like that. Obviously, when you release the bowstring, the bow gains kinetic energy, and then that energy transfers into the arrow. I guess you can say it's the bow. I guess you can say the bow gains kinetic energy. Yeah. All right. And so when you stretch this the bowstring, you let go, that potential energy turns into kinetic energy. All right. No. It's the bowstring definitely moves, right? So before all that energy transfers into the arrow, the bowstring does move as well. And so the potential energy of the spring is given by this formula. PE sub S is equal to 1/2 kx squared. As you can see in the bottom right hand GIF, I found it funny. I'm not sure if you guys have the same humor as me, but I found it funny because the guy doesn't have an arm, right? He's using his leg to shoot the arrow, but then the MC, the guy that goes to award him and shake his hand, he goes for his arm, even though the guy doesn't have an arm. Then he goes on to shake his leg. But that's just me, right? I think this image also shows you what's going to happen, right? Pretend that this is the equilibrium position. I mean, not pretend, it is the equilibrium position, right? So that's the natural state. That's the equilibrium position. And then once you stretch it, that's X, right? X is basically how far you are from your equilibrium position. And K is your spring constant. We learned this yesterday. Talked about this yesterday. This is your attendance question. Yes, it is. Let me just type it. Yep, already typed it, guys. Guys, again, this question is about what is the mathematical relationship between the deformation of the spring and the potential energy the spring gains. Again, the formula for potential energy of a spring is 1/2 kx squared. And the deformation is X, and potential energy is PES, P sub S. Okay, so what's the relationship between X and PES here? The poll says something broken. See if you can refresh it. It's not loading on Google for you. Try and refresh. The link seems correct. Link seems correct. I'll pause the timer. You guys got like 20 more seconds, okay? 19, 18, 17. 10 seconds. This is your attendance poll, by the way, guys. This is your attendance poll. You gotta go. Okay. All right. If you answer the poll, it's fine. You got 5 seconds. 4, 3, 2, 1, 0. Locked. Not working for you. This is the only class that literally has so many problems with the poll. All right. Good. This is the most class. This is the class with the most correct answers. It is an exponential. Exponential meaning that your graph is going to look like a U, right? As you put this as spring goes through its equilibrium, I'll mark you here, Asim. As the spring goes through the equilibrium position, right? Your potential energy follows this curve, this U curve. All right, so that's how it is, okay? Also exponential, if you've seen this in math before, y is equal to x squared, that's basically a parabola, right? So now there's something really important here is that this is not including friction, right? This is very ideal. This happens in problems that we basically ignore friction. In real life, some things follow another path. In real life, the curve might look like this, right? That's what the curve might look like in real life. Because atoms do bump into one another as you stretch things, more or less. Electrons, various things. So let's take a look at this PhET simulation. Let's put the energy graph. Let's do applied force, displacement, equilibrium, value. So as I push it, as you can see, my potential energy follows a parabolic curve, right? As I continually compress the spring, I gain a lot of energy. Let's increase the spring constant, right? Let's keep pushing the spring. As you can see, as you compress the spring, you see that the potential energy increases at an exponential rate. Same thing if I were to pull the spring, right? My potential energy would increase at an exponential rate. Exponential rate there. All right. Cool. All right. All right. All right. All right. Let's go. Let's get through these practice problems. Okay. Let's get through these practice problems. You know the drill by now, guys.
The kinetic energy is 16 joules.
Kinetic energy is 16 joules.
Distance is 1 meter.
Distance is 1 meter. You're correct, by the way, Abigail. The work you do is the work being done on the spring is 16 joules. And what'd you say?
Yeah, I said distance is 1 meter.
Okay. You're all measuring the same joules. This cart, when the cart hits the spring, the cart is doing work on the spring. So you can say that the work done on the spring is 16 joules. While the kinetic energy of the cart is 16 joules, the cart will eventually do work on the spring. There's something that, this is a misconception I notice pretty much all students make, or rather all students have, is that students don't realize that you're measuring all of these things in joules. No matter if you're potential energy or kinetic energy, you're measuring it in joules. They're all basically the same thing. So it's not a far off concept to assume that if work is measured in joules, that you can basically substitute work for kinetic energy. The cart will do work on the spring. What else do we know, guys? Or rather, what else do we solve for? Solve for K. So the only formula that you guys have learned so far is 1/2 kx squared. But how does that make sense, right? We don't know what potential energy of the spring is. How do we find out? What is it? What is it going to be? I'll be pleasantly surprised if you figured it out. I'll be happy, actually. I'll be happy. It means that you understand the concept of transfer of energy. Why is it 16? It would travel the same distance back. No, it's not. That wouldn't be the reason. So let's actually take a look. The kinetic energy of this card just before it hits the spring, 16 joules. My gravitational potential energy is 0. It's frictionless, so no matter what I do, I'm not losing any energy due to friction. And my potential energy of the spring, well, I don't have a spring. My potential energy is 0. So my total energy here is 16. Now the cart is compressing the spring. That's what it says in the problem. If the cart comes to a rest after compressing a spring a distance of 1 meter, so now the spring is compressed, right? Now the spring is compressed. And the velocity of this cart is 0. What's my kinetic energy at this point? What's the kinetic energy of my cart here when my velocity is 0, right? Because it says comes to a rest.
0.
0. Because that doesn't apply for transfer of energy. Your kinetic energy here is 0. Yeah, that's fine, Asa, no worries. What about my gravitational potential energy? Is my height is still 0, so it's still 0. Again, it's frictionless. I'm not losing any energy due to friction. So where does all this energy go? Where does my 16 joules of kinetic energy go? It has to go somewhere. I'm not losing it to friction.
Does it come back to the cart?
Once the cart starts moving again, but again, we want the spring constant. We want at the moment where the cart has a velocity of 0, where has the energy gone into?
The spring.
The spring. The spring is being compressed. The velocity of the car is now 0. Where does all that energy go into? It goes into compressing the spring. That's where the energy goes into. So your potential energy here is now 16 joules. Right, and now we can solve for it. So we have 16 is equal to 1/2 k, because 1 squared is 1. Anything multiplied by 1 gives you itself. Multiplied by 2 on both sides. 32 newtons per meter is equal to k. All right. That's the answer. Okay. And then the card gains back its energy once it pushes out, right? Right. At this specific moment, all its kinetic energy is now in its potential energy. Right. At this very specific moment. And that's what we care about. Any questions on this before I move on? Asim, I already told you before that I marked you here. All right. Let's do this last practice problem. You guys know the drill. Elastic is just another word for spring, okay? Elastic is just another word for spring. That's really just a proper way of saying it.
Your potential energy is 10 joules.
Yeah, so your spring potential energy, P sub S is 10 joules. What else do we know?
X is equal to 0.2.
Yeah, X is equal to 0.2 meters because you're compressing the spring. What you guys want to find out? You want to
K.
find out. Yeah, you want to find out what K is. Good. I think these are really straightforward problems, guys. I think these are really, really straightforward problems. So at this point, you just plug it and solve, right? So P sub S is 10. K is K, that's what you want to solve for. X squared is 0.2 squared. X squared is 0.04. 1/2 times 0.04 is 0.02. Divided by 0.02. 10 divided by 0.02 gives you 500. That's the answer. Any questions about this? Please raise your hand. Very important, guys. Okay. I think these questions are really straightforward. I think the knowns are really straightforward. Your homework, really straightforward too. All these questions we did in class either yesterday or today. I think it's really straightforward, guys. Let's watch a review video before we go. I'm gonna have to mute that. I actually get copyright striked for that. For that intro song in this YouTube video, I get copyright striked.
About all the things.
Not that I
with
care. I
springs.
don't
Locks,
monetize my
clocks,
videos.
mattresses
I don't have
and
enough
sofas,
viewers anyway.
pens, devices that hold batteries, trampolines, and toys. Springs are so important, they have their own sound effect. In physics, there's a set of scientific laws surrounding springs that involve elasticity, torsion, and force. All of those come into play with springs. That's what British physicist Robert Hooke figured out in the 1600s. Hooke's law helps explain elasticity. It states that the force needed to extend or compress a spring is proportional to the distance that it's stretched or compressed. All springs, whether it's a rubber band or a slinky, have a natural position based on how they're made. Some, like this slinky, are naturally compressed. So when you stretch them, they want to spring back into the compressed shape. A spring on a garage or a porch door are naturally compressed. Mattress springs and springs in some ballpoint pens are compressed springs. Whatever the spring's natural position is called its equilibrium position, where it's either not stretched or not compressed, depending on the type of spring. So here's the equation. F sub s equals negative k times x. F sub s is the spring force, and it's measured in joules.
That's not the case. Spring force is not measured in joules, it's measured in newtons. That's actually a technical error in the video.
Once it's stretched or compressed,
I'm not sure how
much
no one caught this.
the spring moves or is displaced is x, which is measured in meters. The k is called the spring constant, which is
easily provable because I can just do it right now. They say that spring constant is measured in Newton meters. So K is going to be measured in Newton per meter. X is measured in meters, which is basically M over 1. You cancel out the M on top and bottom, and then you get newtons. X is in the Y direction? No, X is just your change in equilibrium position. It doesn't matter. X has nothing to do with the Y direction in this case. X means how far you are from your equilibrium position. It doesn't really matter. You'll learn that you can be flexible with your variables as long as you know what you're talking about. For example, I can just write because a formula is not just variables, a formula is a definition. Because I can write negative K change in Y. And technically I'm still correct, right? I'm still correct. I know what the law means. I know how to use the law. But in the end, you just want like consistent units from everyone. But yeah. Spring force is measured in newtons, guys. Right?
a particular spring behaves. The units for that are newtons per meter. The x is a negative value to show that once the spring is displaced by a force, for it to spring back to its equilibrium state, the displacement is opposite the direction of the initial force. So, if you pull down on a spring, the spring moves downward, but when you let it go, it springs back in an upward force due to the elasticity of the spring. That's the negative kx. This is why the spring force is also sometimes called the restoring force, because it wants to restore the spring back to the equilibrium position. Whenever you do a problem with springs and elasticity, it's always important to remember to note the direction of this restoring force. We're going to use Hooke's apparatus, named after Robert Hooke, to demonstrate spring.
We would use this in class. We would definitely This would have definitely been a lab. All right, this would definitely have been a lab.
And all they can do. To see how much a spring stretches or compresses, let's get some spring action by adding some weight. Remember, weight is the mass times the acceleration due to gravity, g. With weight added to a vertical spring, let's see how much it stretches or compresses. Now let's add a heavier weight and do this several times. Each time you add weight, plot the spring action on a graph with force on the y-axis and displacements on the x-axis. How far does the spring stretch or compress? Check it out for yourself. You'll find that it's likely to be a straight line. The slope of this line is the spring's k constant. You might also discover that not all springs follow Hooke's law perfectly. When the force needed to compress or stretch a spring by a given displacement is linear and abides by Hooke's law, then the spring is considered Hookean. In real-life situations, the ideal springs are called Hookean and non-ideal springs are called non-Hookean. Rubber bands, for example, are non-Hookean. What does that mean? When the force needed to compress a spring by a given displacement is not linear and does not abide by Hooke's law, that spring is considered to be non-Hookean. If a spring is stretched too much, it loses some of its springiness and becomes non-Hookean. In that case, that straight line on the force versus displacement graph becomes a curve. Now, what if we pulled on one of these weights and there was no friction to stop the springing action? It would continue to bounce up and down forever. That same thing is true of a horizontal spring. This is called simple harmonic motion.
We don't care about simple
harmonic
harmonic
motion. We'll
motion.
explore this idea in a later unit. Let's pull the spring away from its equilibrium position. Now, we have spring potential energy since we know it will spring back into its equilibrium position. Here's the equation to figure out the amount of potential energy in the spring. Pe sub s, that's the potential energy of the spring, is equal to 1/2 k, the spring's constant, times x squared. X is the displacement we've pulled the spring away from the equilibrium in meters. And the potential energy is in joules. So we can relate the spring's potential energy to gravitational potential energy. From another segment, you learned that...
All right, that's fine. Anyway, guys, I'll upload a video sooner or later, probably later. But again, guys, your 8 homework questions really resemble the 2 questions from yesterday. They resemble the 2 questions from today. I think the questions are really straightforward. You identify your knowns. You choose one of 2 formulas that you've learned. You either choose F sub s is equal to kx, or you choose Pe sub s is equal to 1/2 kx squared. Choose one of either to solve these problems, and you guys are good to go. Okay, and I'll see you guys tomorrow. All right, see you guys tomorrow.
Mr. Chan, are you there?
Yeah, what's up?
If you don't mind, could